Welcome to the Network Plus Prepcast, your dedicated audio companion for mastering every objective on the CompTIA Network Plus certification exam. This series is produced by baremetalcyber.com. Transmission Control Protocol and User Datagram Protocol are the two primary transport layer protocols used in IP networks. Both function at layer 4 of the OSI model and are responsible for delivering data between applications on different devices. Their job is to ensure that data created by an application on one system can reach its destination and be reassembled in a usable form. While both TCP and UDP serve the same general purpose, their designs are fundamentally different, and understanding these differences is critical for analyzing how traffic behaves, how services are configured, and how network security tools are applied. For the Network Plus exam, you will need to recognize which protocol is appropriate for a specific application, identify associated port numbers, and interpret protocol behavior in real-world scenarios. TCP, or Transmission Control Protocol, is a connection-oriented and reliable protocol. It is designed to ensure that data arrives completely and in the correct order. TCP builds a session between two endpoints using a handshake process to establish the connection. Once the session is created, TCP provides sequencing and acknowledgment features that keep track of every byte transmitted. If any part of the data is lost, corrupted, or delivered out of order, TCP detects the problem and retransmits the necessary segments. This level of control makes TCP well suited for applications where data integrity and reliability are essential, such as file downloads and web transactions. UDP, or User Datagram Protocol, takes a very different approach. It is a connectionless protocol, meaning that it does not establish a session before sending data. There is no guarantee that packets will be delivered, no way to detect loss or corruption, and no built-in acknowledgement process. UDP simply sends data and moves on. This simplicity results in lower overhead and faster transmission, making UDP ideal for real-time applications where speed is more important than perfection. For example, if a few voice packets are lost in a conversation, it is better to skip them than to delay playback. The TCP three-way handshake is the mechanism used to establish a connection between two systems before data transfer begins. It starts when the client sends a synchronization message, called a SYN, to the server. The server responds with a SYN ACK, acknowledging the request and signaling readiness to proceed. The client then sends an ACK message to finalize the process. This exchange ensures that both parties are ready to communicate and agree on initial parameters such as sequence numbers. The three-way handshake also helps protect against certain types of attacks and ensures that connections are only established with responsive systems. Sequence numbers and acknowledgement numbers are essential features of TCP. Each byte of data in a TCP stream is assigned a sequence number, and the receiver uses acknowledgement numbers to confirm receipt of the data. This allows TCP to track exactly which parts of the data stream have arrived and to detect any missing segments. If a segment is lost or arrives out of order, the receiver can request a retransmission. This mechanism ensures that the data arrives correctly and in sequence, even if the underlying network is unreliable or congested. TCP also incorporates flow control and congestion avoidance mechanisms to manage data transmission speed. Flow control uses a technique called windowing, where the receiver advertises how much data it can accept at one time. The sender adjusts its transmission rate to match the receiver's capacity, preventing buffer overflows. Congestion control mechanisms monitor network conditions and adjust transmission rates to avoid contributing to congestion. These features make TCP robust in complex environments where variable latency and traffic loads can impact performance. UDP's simplicity is what makes it ideal for real-time or time-sensitive applications. Because there is no connection setup or teardown, UDP begins transmitting data immediately. This eliminates delays associated with session management and retransmission. As a result, UDP is used in applications where occasional data loss is acceptable but delays are not. Examples include streaming media, online gaming, and voice over IP. In these cases, the small size and minimal processing of UDP headers contribute to lower latency and faster delivery. Common TCP-based applications include web browsing, which uses port 80 for HTTP and port 4943 for HTTPS. Email services also rely on TCP with protocols like SMTP, IMAP, and POP3 all operating over TCP to ensure that messages are delivered accurately and completely. File transfers using FTP or reliable delivery. These applications prioritize data accuracy, and the added overhead of TCP is justified by the need for guaranteed transmission. By contrast, UDP is the preferred transport for applications where a few lost packets will not significantly affect performance. Domain name system queries typically use UDP port 53, where quick response is more important than retrying failed queries. Streaming protocols like Real-Time Transport Protocol and Trivial File Transfer Protocol also use UDP. Voice over IP and video conferencing benefit from the speed and efficiency of UDP, even if it means that occasional data is lost. These use cases show that UDP is not worse than TCP, but rather designed for a different kind of task. Although TCP and UDP share the same range of port numbers, from 0 to 65,535, they represent separate transport layer mechanisms. A port number like 80 may be reserved for HTTP over TCP, but the same number could be used for a different purpose if running over UDP. Applications must specify both the port number and the transport protocol to establish communication correctly. Firewalls and routers must be configured to recognize this distinction, as allowing TCP traffic on a port does not automatically permit UDP traffic on the same port. For more cyber content and books, please check out cyberauthor.me. Also, there are other podcasts on cybersecurity and more at baremetalcyber.com. Troubleshooting issues related to transmission control protocol often begins with examining packet behavior. Because TCP is a connection-oriented protocol, it provides a detailed trail of information about how the connection is established, maintained, and closed. If a TCP session fails to initiate, a packet capture may show that the three-way handshake is not completing. This could point to a blocked port, firewall misconfiguration, or an unresponsive host. If the session starts but then stalls, analyzing window sizes and acknowledgment sequences can reveal whether congestion or flow control mechanisms are throttling transmission. Retransmissions, resets, or out-of-sequence packets also offer clues about where the breakdown is occurring. For the exam, understanding how to interpret TCP behavior in these situations is important for answering scenario-based questions. By contrast, User Datagram Protocol presents different challenges when diagnosing problems. Because there is no connection establishment, packet loss or delay is not automatically reported by the protocol. Instead, administrators must use external tools that measure timing and packet flow to identify issues. Applications using UDP may implement their own methods for detecting dropped packets. But from a network perspective, the burden is on the administrator to interpret metrics like jitter and loss. When a UDP-based service experiences problems, tools designed for voice, video, or real-time traffic are essential for capturing and analyzing performance data. A fundamental distinction between TCP and UDP lies in their efficiency versus overhead. TCP adds multiple layers of logic, including sequencing, acknowledgment, retransmission control, and congestion management. This creates larger headers and more complex state tracking, but results in highly reliable delivery. UDP, on the other hand, adds only a minimal header, consisting of source and destination ports, length, and checksum. It avoids session tracking and control logic entirely. This trade-off is what allows UDP to outperform TCP in applications where speed is critical and where slight data loss can be tolerated without significant impact. Security tools and policies must handle these protocols differently. TCP's stateful nature allows firewalls and intrusion detection systems to track the progress of a connection. They can match the initiation, data transfer, and termination phases of a TCP session and filter traffic based on context. UDP, lacking state information, is more difficult to inspect in detail. Its connectionless behavior makes it easier to spoof and harder to control with stateful rules. As a result, many firewalls block UDP traffic by default unless explicitly allowed. On the exam, you may encounter questions about why a service is blocked or why a firewall rule needs to be defined for both transport types. Knowing which protocol is in use often comes down to the port number and the transport layer. TCP port 80 corresponds to HTTP, while UDP port 161 is typically used for simple network management protocol. A port number alone does not indicate which protocol is being used. That distinction is made based on the context of the communication. For example, port 69 used over UDP indicates trivial file transfer protocol, but the same port would mean nothing if paired with TCP. Network tools must be aware of both the port and the transport protocol to interpret traffic correctly. Each transport protocol has its own header structure. TCP headers are more complex and include fields for sequence number, acknowledgment number, flags like SYN and ACK, window size, and checksum. These headers support the features that make TCP reliable and stateful. UDP headers are simpler with fields for source port, destination port length, and checksum. This simplicity reduces processing overhead and contributes to faster transmission speeds. For the exam, understanding these headers helps explain how each protocol functions and why one might be preferred over the other in different use cases. Multiplexing is another important concept supported by both TCP and UDP. Through port numbers, multiple communication sessions can occur simultaneously over a single device. Each session is distinguished by a combination of source IP, destination IP, source port, and destination port. This allows a server to handle multiple clients at once, each with their own connection or datagram exchange. For example, a web server can serve thousands of users concurrently by assigning a different source port to each client. This principle is essential to modern networking and is often tested on the certification exam. On the Network Plus exam, expect to be asked about which applications use TCP or UDP, which port numbers are associated with each, and how each protocol behaves under different network conditions. You may be required to troubleshoot an application that uses UDP and identify why performance is poor or why a service cannot establish a TCP session. Other questions may test your understanding of header fields, firewall behavior, or transport layer services in the OSI model. Solid knowledge of both protocols, their differences, and their common applications will help you succeed. In conclusion, Transmission Control Protocol and User Datagram Protocol each serve critical functions in transporting data across IP networks. TCP ensures reliable, ordered delivery for services that cannot tolerate data loss, while UDP offers low-latency performance for real-time applications where speed matters more than accuracy. Understanding when to use each, how to troubleshoot them, and how they interact with ports, firewalls, and applications is essential for both the certification exam and real-world network operations. Thank you for listening to this episode of the Network Plus Prepcast, your trusted audio guide to the CompTIA Network Plus certification. This episode was produced by baremetalcyber.com. For more cybersecurity podcasts, books, and resources, visit baremetalcyber.com. Thanks for joining us for this episode of the Bare Metal Cybersecurity Plus podcast. For more episodes, tools, and study support, visit us at baremetalcyber.com. And before you take the test, make sure to check out the practice questions in the book Achieve CompTIA Security Plus SY0-701 Exam Success by Dr. Jason Edwards. They cover every domain and are a powerful way to lock in your knowledge.